Hi everyone, it's Mrs. Summer here. This is lesson 105, Rules for Electron Configuration. In this lesson, students will be able to model an atom's electron configuration using quantum mechanics and apply the Aufbau Principle, Hunds Rule, and the Pauli Exclusion Principle to fill atomic orbitals. If you recall, the quantum mechanical model is the most advanced and accurate model of the atom. It describes with more detail where electrons can possibly be in the electron cloud and explains energy levels using quantum numbers. Electron configuration is a detailed way of showing the order in which electrons fill in around the nucleus. So when we write it with a series of letters and numbers similar to algebra, but in this case, the letters and numbers signify where the electron is most likely to be found. So the number in the front is the energy level. The letter is the sublevel. Is it in the S, P, D, or F orbital? And the exponent is either going to be a 1 or a 2 for the S, a 1 through 6 for the P, a 1 through 10 for D, or a 1 through 14 for F. Because that's how many electrons each sublevel can hold. If you recall, S can hold 2, P can hold up to 6, D can hold up to 10, and F can hold up to 14. In order to fill out electron configuration, we must follow 3 rules: the Aufbau Principle, Hunds Rule, and Pauli Exclusion Principle. Aufbau Principle states that electrons fill energy levels with the lowest energy first. It means that the first energy level gets filled before the second before the third before the fourth. It's basically describing that electrons are lazy, so electrons equal lazy. They're not going to use more energy to fill a 2 or 3 energy level if this first one is open. The second principle is Hunds Rule. Hunds Rule states that electrons that fill orbitals of the same energy level, so the same energy level, will have the maximum number of electrons with the same spin. It's called the empty bus seat rule, or like I like to call it, the COVID-19 rule. If you're getting on a bus, you have a bus here, the door's here, you're right here, and this seat is empty, and so this person gets on, and they're sitting right here. Well, then this other person comes on. I can make it a different color. So this person tries to get on. He's not going to sit right there because this seat is empty. It's going to go right here. So you fill the empty seats first before you're doubling up. Same goes for electrons with Hunds Rule. They're going to fill up here, here, and here first before trying to double up. In this correct version, the 1s has a pair because the 1s orbital can only hold at max 2 electrons. Same goes for the 2s. 2s has a doubled up pair because it can only hold 2 electrons. Then, when we get to the p orbitals has 3 directions, remember? And we have 2 additional electrons to fill up. It's not going to look like this because they're spaced in the exact same energy level, and so they can spread out just like an empty bus seat. The Pauli Exclusion Principle states that if you have 2 electrons that occupy the same energy level, they must have opposite spins. What this is describing is, if we talk about our bus seat analogy again, and we have a seat here and a seat here, and a person gets on here, and another person gets on here, and then we have a third person coming on, where are they going to sit? Well, they're going to have to occupy this space because it's the closest, the lowest energy. So as we put that person on, they are going to have to sit here. But one person's going to be looking out the window here, and one's probably going to look out the aisle here. They're not going to look at each other or talk to each other. The same applies to electrons in the same energy level. If we look, electrons have a negative charge. If both electrons in an energy level are spinning the same way, they would experience too much repulsion and be unstable. If you recall, so if we have an electron here and an electron here, they're going to push against each other because like repels like. How we represent that, though, in our electron configuration is by up arrows and down arrows. So we draw an up arrow to represent spinning one way and a down arrow to represent spinning another way. So if we have more electrons, because remember, in the p orbital, each direction can hold 2 electrons. So, but one electron needs to be spinning up and one needs to be spinning down. If we look over here with our correct and incorrect representations, this is correct because they're both spinning one way and the other one is spinning down. Spin up, spin down, spin up, spin down. Over here, the incorrect, it's incorrect because in this 2s orbital, they're both spinning up. If that was the case, they would repel each other over here and become unstable. Let's do an example of electron configuration together. So the question states, fill in the energy diagram for the electron configuration for oxygen. Then write the electron configuration for oxygen. Well, how many electrons total does oxygen have? We know from our previous lessons that the smaller number, the atomic number, tells us how many electrons in a neutral atom. So in this oxygen, we have 8 electrons that we need to fill in the orbital diagram. So I'm going to start with my 1s, and I'm going to fill in 1 electron spinning up because of Pauli's exclusion principle, and 1 electron spinning down. Now, I filled the 1s or energy level according to Aufbau's principle. I have used 2 electrons so far, so I have 6 electrons left to account for. Now, I'm going to go up to my next lowest energy level, which is 2s. Spin up, spin down, and now I've used another 2 electrons. And I have 4 electrons left. Now I've reached my 2p. So I'm going to spin up, spin up, spin up. I'm going to fill each section of the p before I go back and fill it in, doubling up. Because this, remember, is Hunds Rule. We fill it up, each section going up first, and then, since we still have 1 electron to account for, it now has to double up on a bus seat because the 2p orbital is not completely filled. So if we were writing this electron configuration now, so we filled in the energy diagram, now we need to write the electron configuration. So I'm going to look here, I am at my 1s, and there's 2 electrons in the 1s. So I write 1s2. Then I go up 2s and 2, because there's 2 electrons in the 2s. Then I look at my 2p, and I have 2p, and I have 1, 2, 3, 4 electrons in my 2p orbital. And that's the electron configuration for oxygen. Here is a much neater, completely filled in electron configuration and orbital diagram for oxygen. So let's do another example. So fill in the energy diagram for the electron configuration for copper. Then write the electron configuration for copper. So copper has 29 electrons to account for. So I'm going to start filling in with the lowest energy level first, Aufbau's principle. So I'm going to fill in 1s, 1 up, 1 down. Then I go to 2s, 1 up, 1 down. And then 29, so I've used 4, is 25. You have to keep track of the electrons or you won't realize how many you've already filled. So then with my 2p, 1 up, 1 up, 1 up, then I'm going to come in and fill it in because that was another 6 electrons, and I still have 19 electrons to account for. So my 3s, 1 up, 1 down, 3p, 1 up, 1 up, 1 up, 1 down, 1 down, 1 down. So 3p, so I've used 2, 4, 6, 8. So 19 minus 8, 11. So 4s, 1, 2. Used another 2. I have 9 to account for. And I am left with, so 3d, this is the first time we've gotten to the d orbital. So 1 up, 1 up, 1 up, up. Now I can come back in. So that's another 5. So I have 4 electrons left. So 1, 2, 3, 4. And then I'm at 0. Now for writing the electron configuration, I just go 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d10. We write the 4s2 before the 3d because if you look at the energy, 4s has less energy than the 3d. And here is the previous example, nicely written and diagrammed, way better than I can hand draw on these slides.